Good morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 4, which is the distribution network OPF analysis, and we have studied that how to formulate the distribution network OPF, that is with the bus injection model and branch flow model. So today we will continue with the formulation of the centralized and the distributed OPF algorithm and how to solve them. So first let us see what is the difference between centralized and distributed OPF. First, in case of centralized, you will have a central controller, okay, that has the responsibility to manage the entire network, and that will handle the large amount of data set from the entire network and to take care the network constraint, to take care the operation of each and every grid edge devices. The optimization problem will be formed as that will minimize or maximize or optimize the entire network goal, not only for the sake of few people or few DERs or few customers. That will take consideration for the entire network. So it needs a high computing and a long communication facility. Okay. But the benefit is that it is an easy to formulate. Okay, because you have everything at in one place, so you can foresee the network condition just sitting at one place. So it is very easy to formulate the centralized problem. Second, that is, you can say that is a challenging feature, or you can say drawbacks of the centralized. That is the biased solution. Why you called it biased? Let us say you got data from 10 customers, okay, that you want to do the load shedding. Now, apart from that, let us say 5 customers are very critical customers, their criticality level is little bit higher and 5s are lower level. So, what we will do? To reduce the customer dissatisfaction as a whole for all the customers, the central controller will always try to do the load shed from the less strict or the flexible customers. That means, the flexible customers will suffer more compared to your critical customers, and critical customer may not experience any kind of load shedding. So, that kind of solution if you give, that means you are biased to your critical customers only. So, therefore, centralized algorithm possess biasness. Obviously, they are prone to single point failure and very complex solution algorithm you need. Though the problem formulation is very easy, but the solution algorithm is very efficient, it must be very efficient for solving this huge size of the OPF problem, which has multiple variation of variables, parameters, constraints and objective function. Compared to that, if you have a distributed, what distributed is did? It decomposed the network in few clusters, and every cluster you will have a local controller, and that local controller will optimize only that portion of the network which is underneath of it. Okay. So, the optimization problem only focus on that small microgrid or small network which is present under the local controller. The size of the problem will reduce significantly. So, if you let us say have a big network having almost let us say 10,000 buses, and you segregate that network in a let us say 50 areas of unequal length, then approximately all the area will have 200 buses only, right, 200 buses. So, if that is the case, then if you need to solve in a centralized optimization this 10,000 bus together, now in the local controller you just need to solve the 200 buses. So, the size of the problem has become 1/50th. So, complexity of that problem or solution algorithm efficiency must not be that much high that you need for the centralized problem. So, the low computing, and you need shorter communication because you are just communicating with your local controller. So, the communication infrastructure length will also be small. You will get more autonomy to the microgrid operators or the local controller operators. But they are resilient to single point failure, as we discussed in the last class, and optimality normally attained by through the consensus, because we have seen that local controllers, they communicate with each other. So, with this communication they will reach at the level of optimality when they will agree that the solution they are getting, that is optimal for both of them. Till they will continue their solution, or they are trying to solve the problem repeatedly till they converge to a single point solution. Okay. So, this is the typical overview of a centralized OPF problem. You can see each local devices, sensors, meters, inverters communicate with the central controller following a star topology, and central controller perform the computation and send new optimal commands to the grid edge devices. Okay. So, you can see all the data that are going to the central controller. Then the central controller will process the OPF engine, that means the OPF solution, and then that will be dispatched to the grid edge devices for the control. Okay. So, that is why it is called the centralized optimization. Local agents have lesser computation requirement. You need not have any computation requirement at the local level, because they are sending all the decisions is made by the central controller. Then most optimal decisions can be obtained as the real time scenarios of all the network resources are considered by the CC. What we told, that it has the visibility of the entire network together. So, when you have visibility for the entire network, you can do the take out the best, but that best can be biased. Okay. So, this is the formulation of a linear centralized OPF problem, where you will take an objective function, you have the equality constraints and you have the inequality constraint. That equality constraints will be your power flow constraints and the voltage constraints, and this voltage limit that will go to the inequality constraints. Okay. So, that you have your DR limits and that voltage constraints. Okay. Now, we will come to the distributed OPF. So, what algorithm we have seen in the centralized linear centralized OPF problem, that problem now will convert to the distributed. So, the distributed algorithm says that it decomposes the original feasible centralized OPF. First, remember, the centralized OPF problem has to be a feasible problem. Infeasible problem cannot be decomposed. Okay. So, feasible centralized OPF problem into multiple sub problems by segregating the bulk network, radial network into small areas. So, if it is a large network given here, you segregate it into multiple areas, that is area 1, area 2 and area 3. Okay. Then you decompose them. So, that is your area 1, that is your area 2, that is your area 3. But these areas are interconnected, because you can see that this bus and this bus are connected via this line. So, you cannot decouple them physically at least, but this connection, how you can get rid of it? That you can get rid, because this bus falls, let us say this is bus A and this is bus B. So, bus A falls under area 1 and bus B falls under area B. So, the voltage of the bus B depends upon what is the voltage of bus A, and that will also decide your bus B voltage, that how much power you will feed from bus A to B. So, you need that information. So, this coupling variables or the global variables between the two neighbors, that is that variables which are common between the connecting agents or connecting areas, that we called the global variables. So, each area will have some local variables and each area will have some global variables with its neighboring areas. So, if that global information is shared among the neighbors and then you will reach to the consensus, then you will say that your optimality has been achieved. So, the sub problem is developed at each local level and local OPF problem will be solved. Now, how to solve this? Introducing a coordination equation to bring shared variables of neighboring agents. in consensus considering dummy buses at each area. That means we will disconnect this model by proposing a dummy buses. These are the dummy buses. So, this y2 variable will come as a dummy to y2c in area 1. Similarly, y1 variable will come as y1c as at the area 2. So, if area 1 sends its y1 value to area 2 and area 2 sends its y2 value at area 1, and they can reach to the consensus with this y1 and y2, then you can say that your optimality has been restored. So, this is your y1 minus y1c, y2 minus y2c and y3 minus y3c. That means, whatever data you are sending and whatever data you are receiving, if they both are equal. Okay? That means, the new derived updated data and previously whatever copied data you shared with your neighbor, if you are not updating from the decision, that means you have reached to your optimal value. That is the coordination equation. So, for the distributed OPF framework, if the centralized OPF problem is for a large distribution network is given by minimization of fx subject to the constant gx and hx, then the distributed algorithm assumes above that the centralized problem is a feasible problem and has a feasible solution. That is the primary consideration, and then decompose the entire network into n number of interconnected areas. Okay? Then each area will solve the local optimization problem to determine its local decision variable xh after receiving boundary information zh. We told that if you have a bus here at the area 1 and you have a bus at bus number A and you have a area 2 which is a bus B and they are connected together, you cannot solve this voltage and power value if you do not know the value of VB. Similarly, you cannot calculate VB if you do not know the value of voltage at bus A or power at bus A. So, these global variables has to be shared, and then after the sharing you will solve the local optimization problem to get your optimal decisions. So, each area receives boundary information from its neighbors to update their local decisions. Okay? This process continues till a consensus is attained after among all the areas and no update on the decision is possible. Okay? So, this is a general algorithmic framework of the distributed OPF problem. Okay? So, this is let us say your centralized problem, you decompose into n number of areas. So, each area will share its boundary information to its downstream area and also take information from its downstream area. So, if you see this area 2, it is sharing also to its downstream area and also sharing data to its upstream area. So, you have to send data to the upstream area as well and the downstream area as well. So, generally they are named as parent area and the child area. Upstream is named as parent and downstream is named as child. So, first how to start this algorithm? Initialize the dummy variables with power equals to 0 per unit and voltage equals to 1 per unit. That means, you have to start your optimization, right? You are a local. First you cannot communicate until unless you have something at your hand. So, first the each and local controller, they will assume that they have 0 power sharing with their neighbors and the voltage at the boundary buses, they are of 1 per unit. Okay? With this value you start your iteration till your residual calculation is greater than the tolerance. Then you repeat this step 4 to step 7. So, at the step 4 you will solve your local optimization problem for after getting the data from the parent and the child area of yours. Okay? You are sitting at area 2, you will take data from the area 3 and as well as area 1. That means, you are getting data from your parent area as well as you are getting data from your child area, both the voltage and the power. If you get that, get the solution and get your local solution. Then declare your global variable with your parent and children. Okay? That means, with their global buses or the connecting buses, you share that value with your upstream and the downstream area, and then calculate whether last time whatever you have shared and this time you are sharing, is it the same value or not? Or even whatever data you are getting from your parents and the children, those are same or not? If they are same, that means you are not also updating anything, and also you are not getting any updated value from your neighbors as well. So, that means all are under good condition, all are agreeing with the current solution. So, if that is the case, then you are at your optimal solution. If it is not the case, then you repeat this process till you get that optimal decision. Okay? Generally, the shared boundary information is the bus voltage or phase voltage if it is an unbalanced network, or the power flow at the boundary buses. So, depending upon which data you are sharing, that is voltage or power, and how you are sharing, how you are updating your global variables. So, depending upon that, different distributed OPF algorithms has been designed in last few years. First, the robust one is the alternating direction method of multipliers, that we abbreviate it as an A-ADMM. Then you have proximal atomic coordination, you have auxiliary problem principle, you have analytical target cascading, and equivalent network approximation. So, generally these 5 algorithms are very popular to design distributed OPF problem or to solve distributed OPF problem. So, we will study the famous ADMM algorithm, which is named as vanilla ADMM or traditional ADMM algorithm to solve the distributed OPF. So, traditionally fully distributed consensus ADMM, which is also named as vanilla ADMM, is efficient for solving OPF problems in electrical distribution networks. That has already been proved in multiple literatures. So, this is your problem for each and every area, that you segregate that entire network in h number of areas. So, it will solve the local optimization problem considering the difference between that whatever you are deriving and what you are getting from your neighbors, that difference is 0. That means, whatever last time you considered for your updation, the data you received from your parent or the child, and what you and accordingly whatever solution you got for yourself, if that difference is 0, that means he is also not updating and you are also not updating. So, if that is the case, so that you have to consider, but that is a strict constraint. If you are taking it as a constraint, then it is strict, but that will not be followed in every iteration, that will be followed at when you will reach to the consensus, not before that. So, if you add it as a constraint with the objective function, then your solution will see that it is an infeasible solution, you will not get any solution. So, because of that, we add this as a soft constraint with the objective function with a penalty value and a dual variable, and form the Lagrange equation. That is, your Lagrange will be your actual objective function plus your dual variable with that soft constraint and a penalty function. This is an L2 norm. Okay. That means, if you deviate, how much you deviate from your consensus, that means you are giving more and more penalty will be imposed on you. Okay. So, with this Lagrange equation, each area solves its specific subproblem and exchanges the boundary data such as voltage and power flow with its adjacent area. So, you can see area 1 and area 2 they are sharing, area 2 and area 3 they are sharing. Okay. And these values are voltage and the power, and you have a rho parameter that is called the penalty parameter. Depending upon this value of this rho parameter, that will control the convergence speed of your ADMM algorithm. If you set very high, then it will convert very faster. So, upon receiving the updated information from its neighbor, each region recalculates its loss minimization problem or cost minimization problem and shares the revised data with the surrounding areas. Okay, that means it will update its decision, and that decision it will share with its neighbors. This iterative process continues until consensus is achieved across all areas regarding the shared boundary information. That means, you have no update, you are receiving also from your neighbors and also sending to the neighbors. So, this is the algorithm where you will solve your local information through this problem. You will solve the Lagrange and you will get the local. Then you will update your global value by seeing that your adjacent areas are sharing which data. That means, if you have a two adjacent areas h and k represent the value of the boundary variables calculated by area h and area k respectively, then the shared boundary variable will be updated by the average. This is generally for the strictly for your radial distribution network, because in radial distribution network one area only can have maximum two areas, two neighboring areas. So, if you see area 2, it can have one downstream area, area 3 and one upstream area, area 1, not more than that, because it is a radial architecture. When you will have meshed architecture, at that time you will have multiple neighboring areas, more than two neighboring areas. Okay? But this strictly for your distribution, radial distribution network. Then your dual variable will be updated with this equation. The convergence is tested by calculating the primal and dual residual. That means, your global variables are updating or not. If they are updating, then how much value they are updating with this L2 norm value will calculate, and also with the dual variable alpha. So, we will see the algorithm. Step 1, first initialize the values of the global variables, 1 per unit for voltage and 0 per unit for your power flow. That is the starting, that is the initialization of your algorithm. Then dual variables values will be set to 0 and all the parameters involved in the A-ADMM algorithm will be set. That means, rho values you will set the primal and dual residual tolerance as well, because we have to check this is your convergence criteria. So, we have to set a tolerance value for this criteria as well. So, first start the iteration with I equals to 0, then update the iteration with I equals to I plus 1 and then solve the local optimization problem and you will get the local variables. Then you decide which are your global variables with your neighbors and exchange the boundary information with your neighboring areas. Okay? After receiving that, you update that global variables what you previously initialized or previous iteration data. You update that with your recent data and then also update your dual variable alpha. Okay. So, this updation process at each area is done in parallel. That is why it is a very fast algorithm. That means, area 1, area 2, area 3, area 4, everyone doing their calculation parallelly. That is not a serial operation, it is a in parallel operation. So, all the areas will do their optimization problem or solve their optimization problem in parallel. Then evaluate the primal and dual residual for that particular area. And if these residuals are lesser than their threshold value or the tolerance value, then you got your consensus and your solutions are obtained. If it is not, then you go back to your step 3, update the iteration and continue this process again. Understand? So, this is the vanilla A-ADMM or you can say a traditional A-ADMM. Now, we will see the accelerated A-ADMM, because this process what we have seen as the vanilla A-ADMM is a very slow process. You need multiple iterations to converge to the consensus. Sometimes it takes very huge number of iterations, more than 100, more than 200, 300 iterations depending upon the size of the network. So, you have to make it faster by tuning few parameters. So, it is important to note that the performance of A-ADMM is significantly affected by the choice of the penalty parameter that I told before as well, that your penalty parameter will control the convergence speed of your A-ADMM algorithm and the updation of the boundary variables and the dual variables. That means, if your boundary and dual variables are updated properly, then your A-ADMM algorithm will become faster. That means, you are reaching to the consensus in a very fast manner. So, if you set your rho too high, that means you have set it very high value, let us say 100, 200 values, then it will lead to the oscillations. That means, it cannot catch to the or cannot go towards the actual solution. What will happen? If here is your solution, then it will go to this point, then it will skip that solution and go to the next point and it will see that no, it is not my solution point. Then again it will come back and let us say it has come back here. Then again you will see it went there. So, it cannot hit the solution, it will just oscillate in the neighborhood of the solution. So, that is a possibility, then decrease the likelihood of reaching to the consensus at optimal values. If you set that to rho to too low, means you have set it, let us say 0.0001, very small value, then what will happen? If your solution is here, then it will take a very small step to move forward to that solution. If it takes very small step, then it will take almost 1000 iterations to reach to that convergence. So, that will slow down convergence process. Okay? So, again slow update of the global and the dual variable lengthens your convergence process. Okay. That means, if your updation process of your dual and global variables are not very fast, then if it is slowly updating, then your convergence will become very slow. So, that is why the concept of adaptive penalty and predictor-corrector acceleration components are normally introduced with the vanilla ADMM to make them faster, and that is named as your accelerated ADMM or A-ADMM. So, what is this acceleration components? First thing is that adaptive penalty, that is proposed by Song and Pavlovic, and they suggested the concept of adaptive penalty with the vanilla ADMM. What they say is, instead of using the same penalty parameter for all the local optimization problem, the adaptive penalty approach assigns different penalty values to each area's local OPF. Again, these values are updated in each iteration based on below equation, taking into account the corresponding primal and dual residuals. That means, you will not only assign different penalty parameter values for the different areas depending upon their size, also you update that parameter in each iteration by looking at that how much your global values and the dual variables are deviating from each other. That means, your residuals values are high. So, using these equations with these parameters, you can with these parameters you are setting the updation of the adaptive penalty. If they are updated in between the iteration and you are using that updated value in the next, so sometime it will, let us say your solution price is here. So, at first it will take a very long jump to reach to the proximity of the solution, and if it misses the solution and goes above of it, then it will take a very short updation, and then after some time it will reach to the consensus point. So, you are updating your penalty parameter to control the speed or control the distance travelled by your ADMM algorithm towards the convergence. Okay. Then you have predictor-corrector acceleration component as well. It is originally proposed by Nastrov and implemented by Goldstein with the ADMM algorithm. Okay. What predictor algorithm says? Predictor-corrector acceleration component, it enhances the speed of the algorithm by updating the global and dual variable during intermediate steps. That means, you already updated it by certain values by taking the average of your adjacent areas, but after that also you update it with a value gamma. Okay. And that gamma will also be updated in each and every iteration. So, that will update your global and your dual variable by following this equation. So, if your consensus is attained, then this component will become 0. So, whatever values you have at the present, that is your optimal value. But if it is not, if the acceleration component is only activated if the primal and dual residuals have decreased in the current iteration, that means you are going to the convergence. If you are moving to the convergence, then only it will update the global and the dual variables. If you are not moving to the convergence, then it will do the assigning is something wrong. Okay, then only your predictor-corrector acceleration will be activated when your dual and primal residuals have decreased in the current iteration from the previous iteration value. So, this is the overall accelerated ADMM algorithm. You can see you have to first initialize the global variables and as well as the parameters, what you already did for the vanilla ADMM and also the primal dual residuals. You have to assign and also the extra parameters what you have introduced for the adaptive penalty. So, you first start your vanilla ADMM, do the iteration, you determine your local variables and also determine your penalty parameter value. Okay. Then you share the boundary information, you update the boundary information, you update the dual variables, and now calculate the primary and the dual residuals. If now your predictor corrector acceleration component will be activated if your this time primal and dual residual values are lesser than last iteration values, little bit lesser, and we keep this epsilon value close to your 0.9999. That means it is little bit lesser, but it has to be lesser. So, if it is lesser, then your predictor corrector will be activated and will update the global, then your dual variable and your gamma by following the method. And if it is not updating, then you have to keep the gamma equals to 1, and then your solution will be the previous iteration solution, whatever you have derived, previous solution. You need not to activate your predictor corrector acceleration. After that, you will update your penalty parameter by doing the adaptive penalty, and then this adaptive penalty will be used again in the next iteration for solving the ADMM process. If your residual values are not lesser than your tolerance or the threshold value. If they are lesser than, then go to last step, and you are getting your consensus and the optimal decisions are obtained. So, that is the case for your accelerated ADMM, and we will end here today, and we will continue with the distributed OPF in our next class. Thank you.